Electromagnetic monitoring of modern geodynamic processes, an approach for micro-inhomogeneous rock through effective parameters. This study focuses on microscale anisotropy in rock structure and texture, exploring its influence on the macroanisotropic electromagnetic parameters of all geological media, specifically electroconductivity, relative permittivity, and magnetic permeability. Understanding what happens deep beneath the Earth's surface is crucial for predicting natural disasters like earthquakes and landslides. But how do we study what we can see or touch? One promising approach is electromagnetic monitoring, which allows scientists to listen to the Earth using electric and magnetic signals. This research explores how changes in Earth's crust, especially those related to stress and rock movement, can be detected using these signals. Electromagnetic monitoring is a key non-invasive geophysical technique used to study the stress and strain in the Earth's lithosphere. Methods like magnetotelluric sounding or MTS help to detect both reversible and permanent changes in geological structures caused by factors such as tectonic movements, tides, fluid flow, and human activity. Ongoing monitoring offers valuable data on crystal changes and plays an important role in forecasting geodynamic events like earthquakes. This research introduced an innovative approach to calculating effective electromagnetic properties by modeling real geological formations as layered bioisotropic materials, which exhibit complex magnetoelectric behavior. Using omega-shaped structural elements and homogenization of Maxwell's equations, the study offers a systematic way to derive large-scale properties from intricate microstructures. This method simplifies the analysis of fractured and heterogeneous rocks formations for geophysical applications. Studies have shown a link between variations in electrical resistivity and geodynamic activity in Earth's deep crust. Electromagnetic anomalies, especially those with directional patterns or anisotropy, often coincide with seismic events in active regions like Tian Shan, Altai, Kamchatka, and Kola. These observations highlight the value of electromagnetic monitoring in identifying early signs of geodynamic stress and advancing the understanding of earthquake processes. The main goal of the study is to investigate how modern geodynamic processes like rock fracturing or stress buildup affect the electromagnetic properties of underground rocks. The researchers focus on calculating effective parameters such as electrical conductivity and resistivity using a mathematical framework called Effective Media Approximation or EMAA. These parameters help simplify the complex underground structure into something that can be measured, modeled, and monitored in real time. This research was conducted in the Tian Shan mountain range in Kyrgyzstan, a region with frequent seismic activity and significant geological complexity. The area includes faults, fractures, and active tectonic zones, making it ideal for geophysical study. A key field experiment took place near the Kambarata Dam, where a controlled explosion equivalent to 2,800 tons of TNT allowed researchers to measure how the Earth's electromagnetic properties change in response to a sudden stress event. The team used long-term electromagnetic monitoring, combining field data collection with theoretical modeling. Their work involved tracking how resistivity and conductivity change over time and across different directions. They relied on both natural events like seismic tremors and controlled events like explosions to see how rocks responded. These responses were analyzed using advanced data visualization tools like time frequency series and polar diagrams, as well as simulations of different rock deformation scenarios. To collect electromagnetic data, the researchers used the Phoenix MTU-5 system. This is a highly sensitive device that measures 5 components of the electromagnetic field, 2 electric fields and 3 magnetic fields. The system is passive. It listens to natural signals coming from the deep underground without sending any energy into the earth. It is well suited for harsh, remote, or mountainous regions. It is stated that Phoenix MTU-5 equipment is typically used to record variations in 5 components of the electromagnetic field. The foundation of this study lies in Maxwell equations, which describe how electricity and magnetic fields behave. In the Earth, these fields interact with rocks, fluids, and other underground features. However, the Earth isn't uniform. It's full of cracks and layers. To simplify this complexity, the study uses a method called homogenization, which averages the properties of these materials and produces effective electromagnetic parameters, a way to describe the whole region with a few key values like conductivity tensors. It also is stated in the study that they defined an effective electromagnetic parameter of a media as parameter obtained through the homogenization method of macroscopic Maxwell equations. A key tool in this research is the time frequency series or TFS, which is used to analyze how resistivity changes over time. These graphs help scientists to detect subtle shifts in rock behavior that may not be visible on the surface. When combined with azimuthal rotation measurements and polar diagrams, TFS shows how stress or deformation affects the underground electric environment. The researchers observed that resistivity changes over time and varies by direction. After the Cambarata explosion, electrical resistivity increased in some directions and decreased in others, confirming the sensitivity of the method. The monitoring system also picked up long-term fluctuations linked to lunar tides, fluid movements, and other environmental factors. It is said that experimental data demonstrate clear decreases and increases in electrical resistivity values along orthogonal azimuths, and certain azimuthal rotations make the apparent electrical resistivity most sensitive to simultaneous seismic events. These results suggest that anisotropy, or not just the amount of resistivity, but how it differs by direction, is a powerful indicator of underground stress and change. To understand how resistivity changes under stress, the researchers created 3 rock deformation models. First is the fracturing model, which simulates how rock breaks under stress. This creates cracks that change how electricity flows, increasing anisotropy and lowering conductivity. Next one is quasi-plastic deformation model, which stimulates how rocks slowly deform or bend without breaking. This shifts the electrical properties subtly but still noticeably. Borehole collapse model, which stimulates how rocks behave around a hole or tunnel. Collapse or breakage near boreholes leads to localized but significant resistivity changes. These models help explain what kind of electrical changes correspond to different types of stress, and their results match real-world observation. The implications of this study are significant. Electromagnetic monitoring can serve as a non-invasive tool to detect early signs of geological stress. It can support earthquake forecasting, help monitor infrastructure stability, and improve disaster preparedness. However, there are limitations. Mathematical modeling of bioisotropic media is complex, and environmental noise like rain or vegetation can affect results. Additionally, high-resolution monitoring requires dense sensors placement, which can be expensive. The study presents a pioneering framework for using electromagnetic methods to monitor geodynamic activity. By combining field data, theoretical modeling, and effective parameter analysis, the researchers show that it is possible to detect subsurface stress and rock deformation in real time. The work contributes both scientific insights and practical tools for assessing tectonic activity, infrastructure safety, and earthquake risk. The paper also presents a pioneering approach to geodynamic monitoring by applying homogenized electromagnetic modeling to fracture geological media. This is a new method of early detection and monitoring of hazardous geological conditions that is presented. By listening to the way electricity flows underground, we are learning to hear the Earth's silent signals. These signals can tell us when rocks are shifting, when fluids are moving, and when the Earth might be preparing to release build-up stress. The tools and insight developed in these studies bring us closer to a future where early warning is possible, not just from sensors but from the Earth itself.